Training in Weld Quality Assurance and Quality Control. Section 4, Discontinuities and Defects. Topic 5, the common causes of discontinuities related to weld and base metal properties. The objective of this topic is to be able to identify the common causes of weld and base metal discontinuities related to their properties. Weld quality depends on understanding and ensuring that the materials specified for a job are used. The weldability of metals depends on many factors, which include physical properties, alloy content, welder appeal, and the ability to meet the specified service requirements. Because of these, it is important to be able to identify the types of metal before they are used in fabrication. Let's look at a piece of bare metal. It may appear brownish and dull, or it may appear grayish and shiny. Color is one of the physical properties of a metal. Now, lift a piece of metal. It may seem to be either heavy or light. This property is referred to as its density. A bar of steel is more dense than a same-sized bar of aluminum, and is therefore heavier. Now, try to bend a thin piece of metal. It may bend with little effort, or it may resist bending. The ability to bend or twist without breaking is known as ductility. Metals have many other properties which help to classify them, but for the purpose of this discussion, we will concentrate on the mechanical and chemical properties of weld and base metal. Mechanical properties determine the behavior of metals under applied loads. These include tensile and yield strength, ductility, and impact strength. These properties are critical to the overall quality of a weldment. If any are not in conformance to the design requirements, then weld or base metal failure can occur. Because of this, it is important for the engineers to first verify the type of base metal and then select a suitable match of filler material. The Quality Control Department then makes sure that the specified materials are used. The minimum tensile strength of a metal is the greatest normal load per unit area that a material can withstand without failure. This minimum tensile strength is normally stated in terms of stress. Stress is equal to the force, in pounds, applied to the specimen and divided by the cross-sectional area in terms of square inches. Tensile strength is measured in thousands of pounds per square inch and is important to know when selecting a filler metal, since the use of an incorrect filler is the most likely cause of weld metal-related defects. For example, if a weld has a tensile strength of 70,000 pounds per square inch, but the base metal's tensile strength is 110,000 psi, then the weld is obviously weaker and prone to failure at loads over 70,000 psi. Yield strength is also a measurement in pounds per square inch in which a material under load exhibits a measurable, permanent elongation. Metals with high yield properties have the ability to be forced or stretched out of alignment and return to their original shape once the load is released. A submarine is a good example of a weldment needing a high yield hull in order to withstand the pressures and stresses of the deep. Ductility refers to the ability of metals to stretch, bend, or twist without cracking or breaking. A metal with high ductility, such as copper, will fail or break gradually as the load on it is increased. A metal of low ductility, such as cast iron, fails suddenly by cracking when subjected to heavy loads. The ductility of a material can be expressed as a percent of elongation, that is, a percentage based on the difference between a material's original length and its final length after subjection to a pulling stress. The percentage of elongation can be obtained by subtracting the original length from the final length and dividing the difference by the original length. This result is then multiplied by 100. Impact strength means, as the name implies, the ability of a material to withstand sudden high-load shock at varying material temperatures without failing. It is also called toughness property. A bridge is a good example of a weldment needing a specific impact quality in order to withstand sudden loads of traffic and weather conditions. Some materials, such as steel, lose toughness properties at low temperatures. These materials will behave in a brittle fashion when subjected to an impact energy. Base and filler metals are tested to determine their toughness properties, which are specified in terms of foot-pounds per degrees Fahrenheit. For example, 20 foot-pounds at minus 20 degrees Fahrenheit. A material specified as having this toughness property can be used in applications as low as minus 20 degrees Fahrenheit where impact loading is required. Filler metals must match the base metal toughness property to prevent failure at low temperatures. If a weld has an impact quality of 42 foot-pounds at minus 20 degrees, but the base metal quality is 101.5 foot-pounds at the same temperature, this weld would be weaker and prone to failure at low temperatures. Besides mechanical properties, metals also have chemical properties, which refer to the presence of additional elements, such as carbon, silicon, phosphorus, nickel, sulfur, chromium, and so forth. The nature and amount of these substances can affect the performance of the material. For instance, a steel with a high content of nickel and chromium, such as stainless steel, has the property of corrosion resistance, which hinders oxidizing and rusting. Chemical plants, food processing industries, nuclear power plants, refineries, and offshore oil platforms are typical users of corrosion-resistant metals. Therefore, it is important to ensure the proper match of base and filler metal. An improper match may create insufficient strength and inadequate corrosion resistance, such as welding a 400 series stainless steel with a 300 series filler metal. The mechanical and chemical properties of both could differ enough to cause the weld to fail. As mentioned earlier, verifying the type of base metal to be used is important, but it is equally important to inspect the material for any structural type flaws. They should be inspected for such things as laminations, seams, and laps, as well as rough surface conditions and tears. These discontinuities originate at the steel mill when the iron ore and alloys are melted in the blast furnace. From the furnace, the iron becomes solid ingots with some non-metallic inclusions and porosity. It is these inclusions that cause laminations, seams, and laps once the iron is worked. Metals with any of these flaws should be repaired prior to use or replaced if any of the discontinuities exceed allowable limitations. Rough surface conditions such as pits, gouges, or tears should also be inspected to see if the material is usable or not. There are many parties involved in the control of materials. The design engineer is the one generally responsible for specifying what type of materials are to be used in accordance with the service requirements of the finished product and the applicable codes. The welding engineer provides the purchasing department with the requirements for filler materials. The purchasing department then prepares the purchase order based on the requirements of the welding engineer. The weld inspector is now responsible for verifying that the specified materials are indeed being used, and also provides feedback of any discrepancies to the welding engineer. For example, when an improper filler metal has been received. Communication of filler metal information through standard specifications is essential for obtaining suitable weld metal properties. Filler material properties such as strength, ductility, impact, and corrosion resistance should be considered when selecting a filler. As a rule, the strength of the deposited weld metal should match or slightly exceed that of the base metal. There are several criteria governing the proper selection of a filler metal. These are base metal mechanical properties, base metal physical properties, base metal chemical composition, and service conditions and specifications. All of these must be considered collectively when selecting filler metal. The American Welding Society has published a series of specifications that govern filler metal mechanical and chemical properties, methods of manufacture, storage, and classification. These specifications range from A5.1 through A5.30. An example would be A5.5, which covers the specifications for low alloy steel electrodes. The American Welding Society's classification system makes it relatively simple to select proper filler metals. For example, a typical shielded metal arc electrode might have a classification number such as this. The first letter E refers to electrode. The next 2 or 3 numbers indicate the minimum tensile strength of the weld deposit in 1,000-pound increments. In this case, 80,000 pounds per square inch. The next digit refers to the position capabilities of this electrode. The fourth digit indicates the type of flux coating and welding current characteristics. Some classifications also have a suffix, which refers to the chemical composition of the weld metal deposit. For gas metal arc or gas tungsten arc welding, the system is similar, but the prefix ER indicates that it can be used either as an electrode or as a filler metal rod. The next 2 digits indicate the minimum tensile strength in thousands of pounds per square inch of the weld deposit. The letter S is used to designate a solid, bare electrode or filler rod. And the suffix is used to indicate a particular classification based on the electrode's chemical composition as manufactured, as well as its usability and the shielding gas required. For flux core arc welding, the E designates an electrode. A single digit is used to indicate the minimum tensile strength of the weld in 10,000 pounds per square inch increments. In this case, 70,000 psi. The number just before the T indicates the position of welding. The letter T designates a tubular composite electrode with a powdered flux core. And the suffix indicates a particular classification based on the chemical composition of the weld as deposited, the shielding gas to be used, and the usability of the electrode for single or multiple pass applications. The welding procedure should list the proper filler metal to use by the American Welding Society specification and classification numbers. As mentioned earlier, the use of an incorrect filler metal is probably the most common cause of weld-related defects. Whenever the properties of the filler metal differ from those of the base metal, the quality and overall strength of the weldment can be affected. It is the responsibility of the Quality Control Department to assure that the specified materials are being used. Weld quality control does not stop with the verification of base and filler materials. In fabrication, conditions still exist that can bring about failure of the weld and base metal. Conditions including lamellar tears, excessive spatter, and arc strikes can occur in or on the base metal during welding operations. Lamellar tears are most common in heavier weldments. They are separations found within or beneath the heat-affected zone. They occur when the through thickness of the plates cannot withstand the pulling effect of the shrinking weld during cooling. Lamellar tears generally occur in areas of the base metal where inadequate refining is present. To minimize or prevent lamellar tearing, ensure careful inspection of the materials prior to welding. Make sure that the welding procedure is being followed, and attempt to design joints so that shrinkage stresses are brought more in line with the work direction of the material. Excessive weld spatter is a common appearance problem associated with welding processes in which metal transfers through the arc. It appears as metal particles which do not become a part of the weld, but adhere to the weld and base metal at random. Spatter does not affect the strength of the weld, but does produce a poor appearance and increases final cleaning costs. Excessive spatter can be controlled if the current and voltage is kept within the recommended range for the type and size of electrode, if the correct polarity is used, the proper arc length maintained, and arc blow is reduced. As mentioned in earlier topics, arc strikes are a remelting and changing surface profile resulting from an arc. They generally occur outside the intended weld area and can be caused either by the welding arc or by an improperly secured ground connection. Arc strikes create small, localized areas of remelting, hardening, and undercutting, which can lead to the formation of cracks, depending on metal composition. To prevent arc strikes, assure that the ground connection is secured tightly to the work, and take care to strike and break the arc only in the intended weld area. Keep in mind that weld discontinuities always exist, but may not always be defects. Quality control personnel must locate discontinuities and decide whether they are acceptable or are defects. The use of proper tools, knowledge of the size and location of defects, and reference to the code or specification for the job will aid in making these decisions.